All right, why don't we go ahead and get started. So welcome back everybody to EE290C. Just a few administrative things before we sort of dive back into the material. So hopefully, as you guys all know, the homework is actually due tomorrow at 5 p.m. How many of you guys have actually started the homework? Okay, good. Finished? Sort of? Okay, well, so it shouldn't be too bad, but obviously if you haven't started, then you definitely want to get going on that now because you've got like 24 hours or something like that. It takes a little bit of time just to figure out what's going on. By the way, any questions on the homework before we sort of move on with other logistical stuff? Everything's clear? Okay, I'll take that as everything is perfectly clear and you're totally ready to go. Just in case you're not, I will be having office hours tomorrow morning, so I'll be doing that at 9 a.m. just in my office in Corey. So feel free to come by and grab me if you have any questions or anything like that. The other thing that I should mention is there will be no lecture this Thursday. I just have to give another talk, and I think we're still sort of doing okay material-wise, so we'll just skip on it for this Thursday. But I will be posting the first phase of the project fairly shortly, because that will actually be due fairly soon. This first phase will be sort of fairly simplified. Probably I'll just have you do some, let's say, planning or maybe some initial modeling or something like that. But definitely be on the lookout for that because from here on out it's actually really going to be all about the project in terms of both the material we're talking about as well as sort of what you're going to be focusing on in terms of homework and things like that. So make sure you stay on top of that. Yeah.
When are you thinking of having that one due?
So I forget exactly when it is, but I think it'll be like the first phase will be due right before spring break. If I'm, let's say, a day or two late in posting it, then I may push it, beyond that point. But that first phase will probably be mostly like something just to make sure that you've actually looked at it and started thinking about it. The second phase, however, will be sort of fairly, let's say, real, because at that point you should already be sort of ready to do a presentation in class on stuff. And also I'm going to be I split it into 4 phases like this, if nothing else, just because I want to make sure people actually start, because this will be a substantial enough project that if you don't start early enough, then you'll have no hope of finishing at the end. So that's kind of why I phased it into 4 pieces like this. The first couple may be, not that big, but again, this is really just to make sure that, you actually get going on stuff and we have a good shot at really completing it all. Other questions before we sort of keep going on the material, or? Okay, so if there's no other questions, then let's actually go ahead and sort of dive back into the material itself. So last time we were talking about adaptation, and we actually got sort of a bit farther than this, but I wanted to sort of do a quick review. So we talked first about just how you'd adapt the continuous time linear equalizer. Then we started talking a bit about how you'd adapt sort of FIR filters. And that was really all about LMS, or least mean squares. So the intent here is, by the way, not for you to recopy anything that's written here. This should have already been basically what we wrote last time. But this is just to sort of briefly review and kind of remind people. And also what I'm actually going to do is sort of walk through a couple of examples, because there was a couple of questions last time about how you shift various vectors relative to each other. And I think actually the easiest way to see that is really by going through a couple of examples. So the whole trick with LMS was basically that at the end of the day, if you just looked at sort of what it took to minimize the mean squared error, and you sort of basically just took the derivative of the error, then when you take the derivative of the error, sort of something nice happens in that you can figure out that the direction you need to move in is always essentially the instantaneous error times the sort of instantaneous value at the input of the equalizer. Okay, so basically kind of what you're doing when you set the derivative equal to that value, or rather I should say when you set the sort of steps that you take to be equal to that value, that's kind of equivalent to saying that you're going to set the derivative to be equal to 0. Which means that, if you've done things right, should be driving that sort of mean squared error to the minimum possible value. Okay? So that's really sort of how it works. In this particular example, this happens to converge to the MMSE solution. And the reason for that is because when you correlate your errors against that sort of input to the equalizer, both of them actually contain the noise. So you actually do see the effect of the noise, and you try and minimize that. We'll see that in more detail in 1 second. But keep that in mind, because in 1 second I'll show you sort of what happens when you don't actually have some of these signals available, which then ends up forcing you to converge to the zero forcing equalizer, to the ZFE instead. Okay? So just because I think there was a little bit of confusion last time, and I apologize you guys don't have any space for this, you can grab some paper on the side or something like that to write this down if you'd like to. But what I wanted to quickly do is just walk through one fairly simple example of how these vectors and things work out, just to make sure it's sort of clear to everybody. Okay? So let's just pretend that, I have some transmitted vector. And what I'm going to do is I'm going to index everything by time, because remember, in reality, all of these things are being updated every clock cycle or something like that. Okay? So let's say I have my transmitted vector of data, which in this particular case, I'm just going to keep track of 3 pieces of data, and you'll see why I chose 3 in 1 second. So if I say x tx of 1, then sort of like my current data bit is d of 1. My previous data bit is d of 0. And the data bit before that, let's call it d of minus 1. Okay? And again, you'll see why I sort of labeled things in this way in 1 second. Okay, so now if I look at my received signal, and remember this u rx is just what's actually going into the equalizer. Okay? That sort of, by definition, is just going to be essentially some u of 1. So u of 1 is like the analog input in the equalizer at time 1, meaning associated with data 1, plus some noise at that time. Okay? And then if I looked at what it was 1 bit time ago, then that would be u of 0, plus, and actually let me just label this to be more complete, that's urx of 1. Okay? 1 bit time ago, it would have been u of 0, plus vn of 0. Okay? So here I've happened to choose only 2 of them, because in this particular example, I'm going to choose a 2-tap equalizer. But if I had more taps in my equalizer, I would just extend the length of this u vector as well. Okay? So then also, just to be clear, my equalizer is just going to be some w0 and w1 like this. Okay, so w0 is kind of like the cursor tap, and in this particular example, w1 is the first post-cursor. Okay? Okay, so now, and maybe just to see if you guys are getting it, what would be the error at time 1? What would that be? I heard somebody sort of whisper it. And just as a reminder, the error is always defined as it's the output of the equalizer minus the sort of ideal transmitted symbol. Okay? So what is the error at time 1? Given that my equalizer has 2 taps like this, and that my input into the equalizer was this urx at time 1. So what is the error? What's the analog value of the error? Yeah?
W equalizer transpose times urx of 1 minus x.
Okay, that's right. So it's W equalizer transpose, and so I guess I'll actually write it out. It's this times urx of 1 minus which data bit am I subtracting it against? What's my reference?
xtx of 1.
Yeah, it's basically, well, so to be more precise, this xtx is a vector. So it's actually minus d of 1. Okay, in this particular example, I'm assuming the channel has no delay. Okay? So that's why I'm going to do minus d of 1. So actually, I just want to write this out a little bit, because it's actually sort of a little bit more clear if you really actually write it out. Okay? So what is this actually equal to? Like, what's the full value of this thing, just given the way I've defined these vectors? Because remember, this is just a single analog sample now. So I just want to know, what is the value of this analog sample? And it's exactly, you just have to expand the equation there. So, somebody just start saying something.
W0 times U1 plus, well, distributed to VN1 as well.
That's right.
Plus W1 times U0 plus VN0
That's right.
minus D1.
Right, exactly. Just minus d1, right? Okay, so that is the analog value of the error at time 1. Okay? So now if I want to know what is the actual update I should take, meaning which direction should I be changing my equalizer coefficients. And now notice this is actually going to be a vector, because I have to update both W0 and W1 in this particular case. Okay, so now that's just going to be whatever the error at time 1 was, which of course is just W0 times U of 1 plus Vn of 1 plus W1 times U of 0 plus Vn of 0 minus D of 1. That whole thing just times, of course, the U vector, which is U of 1 plus Vn of 1, and U of 0 plus Vn of 0. Okay? this kind of make sense to everybody, or? Okay, so this is just, this was written just to sort of make sure that the time shifts and everything were clear. Now, just to make it even sort of more clear as to how this thing actually works, what I want to do next is basically take this exact same sort of format, but just do it on a specific example where I actually have a channel with a single post-cursor tap. Okay? So everybody done writing this, by the way? I guess, raise your hand if you're still frantically writing. Okay, nobody's still frantically writing. So, okay. So let's actually go. I just want to, again, I'm going to use this exact same framework. But now what I'm going to do is I'm just going to say that the channel itself, it's just a single pole channel. Or excuse me, not a single pole. A single first post-cursor tap. So the value of the main tap is 1. The value of the first post-cursor tap is alpha. Okay? So now just if you sort of keep track of everything again, then your received analog value, what is it going to be at time 1? What is that value going to be made up of? And now I want it in terms of, just remember the transmitted data sequence is something like D1, D0, D minus 1. So what is the received analog value into the equalizer after you go through this channel?
0, 1 alpha? Or?
0, 1 alpha. So I think you're right, but we just have to give it in terms of like D1, D0, etc.
So D1 plus alpha D0.
There we go. It's D1 plus alpha D0 plus just the noise at time 1, right? And then what's the thing before it?
D0 plus alpha D minus 1.
There we go. It's D0 plus alpha D minus 1 plus Vn 0, right? And as before, on my equalizer, I'm just going to use 2 taps. So let me just call that W1. Oops, actually, excuse me, W0 and W1. Okay? So now I'm just going to do the same thing. I'm just going to write out what is that full update that I'm going to do at, as an example, time 1. Okay, now and again, I want to write out the full analog value. Okay? So basically, it's really the same thing as we wrote on the previous thing. It's just that you obviously expand out the U0s and things like that. So if we write that out, that's just going to be W0 times, of course, URX of 1, like the first vector entry, which is just D1 plus alpha D0 plus Vn1. Okay? Then we do the second term over there, which is just D0 plus alpha D minus 1 plus Vn0. Right? This whole thing, of course, we subtract D1 to get, again, our error. And then again, we just multiply this by the analog values of URX of 1, which is D1 plus alpha D0 plus Vn1 and D0 plus alpha D minus 1 plus Vn0. Okay? Now, the reason why I wanted to write this thing out sort of in this level of gory detail was just to sort of point out a couple of, let's say, interesting things. Okay? So again, your update is a vector, meaning you're changing both W0 and W1 at the same time. But if you sort of look inside of it, right, basically I take this entry in the vector, I multiply it by this. I also take this entry in the vector, I multiply it by that same thing. And that sort of tells you which direction you update each one of the individual coefficients. Okay? But inside of those sort of updates, notice you're going to get terms that look something like D1 also times D1. You're going to get things like D1 times D0. You're going to get things like D1 times Vn1. And of course, things like Vn, let's say 0, times Vn0, and so on and so forth. Right? You kind of get all these various cross-product terms. Right? Okay, so, by the way, so notice like those things are, let's say, the instantaneous updates that you apply. But remember, what you're actually doing is you're sort of feeding this into an integration, right? Because basically on every time step, you take that direction, and you add it to the previous value that you had, right? So that's kind of saying that you're going to be sort of averaging or filtering these updates over time, okay? So now here's the question. If I have a term that has, for example, D1 times D1, or even D0 times D0, by definition, what should the average value, in fact, what's the instantaneous even value of that? It's just 1, right? Because the datas are always just plus minus 1. So if I take the data and multiply it by itself, by definition, this should always just give you 1, right? Okay, so in other words, this is just saying if you do dx times dx, that's always 1, okay? Now, on average, if I do d1 times d0, what should I get? Yeah, so why is it 0?
Because half the time you get a 1, and half the time you get a -1. So like there's 2 cases of a 1 and 2 cases of a -1.
Right, so in other words, what you basically said is it should be on average 0, which is correct, because basically half of, assuming that d0 and d1 have nothing to do with each other, then half of the time 1 times 1 would give you 1, -1 times -1 would also give you 1. But of course, on the other half of the time, the signs are flipped, right? So on average, when I add those things together, I should just get 0, which is just another sort of fancy way of saying, as long as d1 and d0 are uncorrelated, that'll just get knocked off by the filter, right? Okay, so how about d1 times vn1? What should happen there? Yeah, it should also be 0, right? Because the noise, that one hopefully is very clearly uncorrelated with the data, right? So that should also get filtered to 0. How about this vn0 times vn0? What should that become?
Noise variance.
Yeah, this just becomes the noise variance, right? And in fact, by the way, even if you have terms like, vn1 times vn0, that's just something like the noise autocorrelation at a one sample time shift, okay? So the reason I wanted to sort of point this out in this level of gory detail is that notice this is now really giving you a hint as to why this is kind of converging to the MMSE solution, right? Because notice all the terms that kind of, are uncorrelated with each other, they just fall out. And only sort of things that have correlated or, they're related to correlated errors actually come into this equation, right? And in particular, it's important to notice that the noise sticks around because you get things like the variance of the noise popping up in your average error term, okay? So we'll contrast this a little bit later. There's other error functions you could choose that would knock off this noise. And so because of that, you wouldn't see it. You'd actually converge to a different solution, okay? Does this sort of make sense to people, or? Okay, so hopefully this is more clear than last time in terms of, how all the time shifts and things like that work out. As we basically got into at the end last time, there's actually a lot of practical issues with how you'd actually do this. And in particular, I said that I gave you this magic reference, which was, the exact transmitted value with like some exact known magnitude and things like that. Well, okay, obviously you don't really have the exact transmitted value at the receiver, because if you did, well, you didn't need the receiver in the first place, right? And then we also talked a bit about, well, how precisely do you really know the error? And it turns out that actually, we're going to want to be lazy and almost not know it at all, except to within the sign of what the error, what direction the error is actually pointing you, okay? So the first thing was, again, we talked about just how do you actually find the error? Well, the error is always sort of relative to the data level. Right? And by the data level, I just mean, what is the 1 that you got, and what is the 0, or equivalently the -1 that you got. Okay? So then we also said, okay, well, we don't really want a high-resolution ADC to estimate those errors. So then we said, okay, well, why don't we just actually put a comparator at either the upper data level or the lower data level, or perhaps even both, and then just look at the signs of the errors. And so indeed, it turns out that you can do what's called the sign-sign algorithm. And actually, it will indeed basically converge to the same solution under, some set of technical caveats which aren't really too important from the standpoint of our discussion. Okay? We also then said that, if we really wanted to be lazy, and remember, a lot of this is all about being lazy because, hey, the channel doesn't change all that fast. So we really don't want to be paying a lot of extra hardware and power for things that, are really just slow kind of tracking things that we need to do. So then we said that actually, in fact, what you could do is even get rid of one of those error samplers, because as long as things are reasonably linear, the errors that you see on the upper level should really be the same errors that you're seeing on the bottom level. So as long as you're willing to just throw away half of the possible updates, no reason why you actually need both of those things. Okay? Okay, so I'll actually come back to that in 1 second. Well, actually, no, I guess I'll do that now. So before we sort of dive into some more of the practical issues, which again we had started talking about last time, the other thing that I want to sort of briefly mention is just when is it that you really can get this sort of MMSE type of solution versus, fortunately or not, in practice, when is it that you end up with sort of a zero forcing type of solution? Okay? So the key thing to sort of realize here is that let's say that I actually had a transmit FIR, right? So in fact, I implemented, and I'll just draw it for the example of one tap here. I implemented something like, my single tap filter over here at the transmitter, right? And I guess I'll draw it as a differential thing. Okay, so this is, let's say, like alpha, and this is, somehow I add these things together. And then I send that over into my channel. And now I have my my receiver. And now I want to somehow figure out how is it that I adapt that transmitter. Okay? So there's, of course, practical issue number one, which is just how do you get data from the receiver back to the transmitter to tell it what to do? Let's not even worry about that. Let's assume that you can do that. Okay? So let's actually draw this sort of in the context of that block diagram we had for the original equalizer, right? So what we're kind of doing is we're saying, okay, well, at the transmitter, what's really sort of coming out of the transmitter is already the equalized analog sequence, right? We're then taking that equalized analog sequence, we're feeding it through the channel, and then only at that point is it actually showing up at our receiver, right? Okay, so now, why is there sort of a practical issue here in terms of actually trying to do the MMSE solution? What's the kind of problem with trying to get the MMSE update? Anybody see it? And by the way, I'll give you a hint, this is kind of the boundary of your receiver right here. So what's the problem?
Transmitter can't sense the noise at the receiver.
Yeah, okay, so you're basically saying the transmitter can't sense the noise at the receiver. That's basically true, but let's even, I just want to be even more specific than that. At the receiver, what's the only sort of information that I have?
ERX.
Yeah, the only thing that I have at the receiver is unfortunately equivalently what's sitting right here, right? In other words, all I have is what happened after both the equalizer and the channel, right? But I don't have what happened before the equalizer, right? And in particular, I don't have any noise that went into the equalizer. All I have is, what came out of both the channel and the equalizer, plus some noise that I'm going to be adding to it, just from, my own receiver or from my termination or whatever it is. Okay? So the practical issue here is that basically you don't actually have the input available to you to check what was the noise going into the equalizer so that you could tune the equalizer based on how much noise was actually going into it, right? So in other words, what this is basically saying is that if I want to measure some error signal here, the only error signal that I really kind of have available to me to measure against is just what's the analog input, what's the analog input into the receiver, again, after the equalizer, and then just compare that to sort of my, again, ideal transmitted data. All right, that's kind of, and by the way I compare against the ideal transmitted data is just I assume that my receiver is getting the right bits in the first place. And so if it's getting the right bits, then at least I can compare sort of the analog inputs against my received bits, which hopefully are the same as the transmitted bits. Okay? So if we just write this out, again, sort of using the notation that we had done before, what we're basically saying is that the update equation that we're going to have to use in this particular case, so like before, we're just going to take whatever the previous equalizer coefficients were and then add some update to them. But now this time the updates we're going to have to make are, essentially we're going to take the error signal, which again is going to be measured relative to the received data. And now kind of the only thing we can really correlate it against is also the sort of ideal received data, right? In other words, we have to take the analog error and correlate it with the received digital value. Whereas remember before, we were taking the analog error and correlating it with the analog input into the equalizer. Okay? So now, I guess this is perhaps obvious based on the title of the slide, but if you do things this way, what will this actually converge to? What are you forcing, what are you forcing to sort of become 0 in this particular case? What's inside of that error term? Let's just do, again, the two-tap example. What's inside of that error term? What does it contain? Not a trick question, by the way.
So you've convolved the channel with the transparent data.
Yeah, so inside of this error term, and let's again just do a two-tap example. Right, that error term is just going to be something like W0 times D0 plus alpha D1 plus VN1 plus W1 times, sorry, did that wrong. D1 alpha D0, there we go, D0 plus alpha D minus 1 plus Vn0 minus D1, right? Okay. What am I multiplying this thing by? Let's say for the, to update the first transmitter coefficient.
1d0.
Yeah, so I'm going to be multiplying it by the vector D1, D0. Okay, so when I multiply that thing by D1, is there any hope for me to see what the noise variance is? No, right? Because when I multiply D1 by the noise, both here and there, guess what? On average, it's just going to get knocked out, right? Because there's no correlation there. The only terms that will be left is correlation between D1 and D1, and of course, the correlation between D0 and D0. Okay? So in other words, what this is saying is that you're completely ignoring the noise. The only thing you're going to do is basically try to drive anything associated with the data to be 0. That's just another way of saying that in this particular instance, you're just going to be trying to kill the ISI completely. Okay, because there's no noise to stop you from just going after completely killing the ISI. Okay? Does this kind of make sense to people, or? Okay, so in the context of a receive, linear equalizer, this is actually, kind of bad news, because it says that if you had, a transmit linear equalizer, this is kind of bad news because it says that if you want to do transmit linear equalization, unless you do some other, let's say, more clever things where you have, some training sequence and you sort of, alternate between training and real data, basically really hard to actually do MMSE. Okay? But there is actually one sort of type of equalization at the receiver where it turns out that doing this is actually exactly what you'd like to do. So anybody have any thoughts as to what type of equalizer you'd actually really would like to completely kill the ISI?
DFE.
Yeah, DFE. Right? Because remember, with DFE, I don't really care about the noise in the first place because there is no noise enhancement. Right? So it turns out that if you're adapting the DFE, this is exactly the kind of update that you would use to adapt the DFE. Right? Because again, in the DFE, you want to make sure that it actually does completely kill the ISI. Okay? So that's kind of a, let's say, a good news, bad news story. If you're using this with a transmitter, you're stuck with 0 forcing. If you're using this with a DFE, well, great. I have 0 forcing. That's exactly what I wanted. Okay? So again, you should notice that the update equations you use for, let's say, for example, a receive linear equalizer versus a receive DFE are different. Because in one of them, you actually completely want to kill the ISI. And the other ones, you want to do a balance between how much noise you have and how much you're correcting for the ISI. Okay? Does this make sense to people, or?
So the major difference is basically the equalizer itself doesn't see any noise. So that makes it a ZFE.
Yeah, so you're saying the difference here is that the equalizer itself doesn't see any noise. It's really more that, unless I do something, let's say, funky, I really don't have the analog input into the equalizer, which includes the noise. Right? All I really get is the analog output of the equalizer with noise. Right? So that's really the main distinction. Right? If you look at sort of this block diagram over here, here I've got noise going into the equalizer, and I can really tap off and look at what is the signal plus the noise into the equalizer. Unfortunately, when it's on the transmitter, all I've got is what happened after both the equalizer and the channel, and then adding noise to it. Right? So I really don't have that analog signal to correlate against. That's really the problem.
So assume if you have an analog transmit, you have some analog noise, then you are basically doing MMSE just for that.
Yeah, okay, so you're right that if the noise was all on the transmit side, then you are sort of doing an MMSE for whatever noise was... Oh, no, actually, I'm sorry. That's even not actually true. And the reason is, so you were saying that if I had an analog transmitter and there was analog noise on the transmitter, that you'd be knocking that off. Unfortunately, even that's not true, because notice my reference doesn't know anything about the noise on the transmitter, right? Because the only way I get that reference is by making decisions on the receiver. And if those decisions have the value of that noise, then I'm sort of making errors to begin with. You see what I mean? Yeah, it's a good question. Other questions on this, or?
Could you explain from the first equation there, how does it exactly the same as the DFE? I thought they're different.
You mean the ZFE or?
DFE.
No, so all I was
it's
saying here is
CFE,
that
isn't it?
this update equation, if you were trying to train the DFE, then this is indeed a good update equation for you to use. Because this would force the ISI to go to 0.
But in DFE, you also do not have x of tx, right? You
Oh,
only
okay.
have
So
estimate
the
of
way I
of
have
tx.
x of tx
Yeah.
is by assuming that I received the correct data bit. So you're right, I don't really technically have the transmitted data bit, unless, of course, I made the right decision, which we're going to have to assume in any case because the DFE was recursive to begin with, right? Does that make sense? Or?
Okay.
Yeah.
How can you do this adaptation if your channel is really bad? If you
Ah,
can't
okay.
just compare-
So this is let's say a classic question. The question was, how can you do this adaptation if the channel is really bad and you're just making mistakes all over the place? The slightly hand-wavy but turns out to be relatively technically correct answer is that, as long as I don't care how long it takes me to converge, as long as I'm making the right answer most of the time, I'll get there eventually, right? So all that really has to happen is that more often than not, I make the right answer, and eventually I'll converge to the right direction. Now again, there's some technicalities about what I'm saying in terms of proving the convergence and things like that. But basically, that's kind of the intuition behind why even if you have a pretty crappy channel to begin with, you can still actually get this thing to converge. It's a great question. By the way, if that's really bad, then you can even do things like a known training sequence where you don't even deal with the actual received values. You just know what the training sequence was and things like that. But even without doing that, you can actually still, practically speaking, basically get it to converge. OK, so unless there's more questions on this, now we can sort of, there are more questions. Great. Yes?
So can there be more than one point of convergence?
OK, so yes. So this is now starting to get into some of the technicalities. If you really do, let's say, the sine-sine version of the loop, there could actually be more than one point that you converge to, because the only thing you're really enforcing is that, on average, the number of ones is kind of the same as the number of so-called zeros. But the good news is that the point that converges to is usually close enough with respect to, let's say, the real solution that you basically don't care. It is possible, and by the way, sine-sine loops in general are just really hard to prove exact characteristics on. But practically speaking, I've never seen that really be a problem. It's a great question, though. Yeah?
So I'd imagine it would still kind of dither about the values. Do you lock it after it's settled?
Okay,
is it better
great
to
question.
lock
So we're
it,
actually
or-
going to talk some more about this in 1 second, but you're absolutely right. This does tend to dither around, right? And that's definitely something you're going to have to include, because you're never going to get this exactly right. Okay, so we're going to talk about that. That's kind of my last slide here. That's a great question. That does actually bring up another point which I do want to mention, which is, especially if you do these sort of sine-sine types of loops, now your updates are really coarsely quantized, right? So what you're going to want to tend to do is not just sort of take them and directly apply them, but somehow average them out even further, right? So as an example, what you'll often do is, also, by the way, you don't typically want to run this thing at 10 or 20 gigahertz or whatever it is. What you'll usually do is you'll deserialize the data and the error itself, do some processing kind of in the lower frequency domain on those error and data samples to sort of figure out which direction you should go. And then as an example, just average over the entire block. As an example, let's say maybe the block of 10 or the block of 20. And then maybe based on the entire block, only if a bunch of them said to move one direction or the other, only then really apply the update. Okay? So there's actually a lot of, let's say, details on how you really build these things and how you do the filtering and stuff like that to try and reduce the sort of dither that you get. Another way of doing it is this, you may have way higher resolution in like the counters you use to estimate these things than you do in the actual DACs you use to implement them. That's another way of just sort of trying to say you're going to try and average out a whole bunch of these updates before you really make a change at the output. But we'll come back to exactly the issue you're asking about because it is actually a very important issue. It's a great question. Other questions on this? Or? Okay, great. So we did start talking about, last time we said that, there was always this sort of practical issue of I kept talking about this error, reference level, but there was no real error reference level. Like somebody has to actually come up with it, right? And so we said there was kind of two ways you could do that. One was to put some variable gain amplifier in front of everything, and then drive everything to some known reference level, or do the reverse, which is again kind of the lazy man solution, which is just say, well, okay, I don't really know what the level is, but let me just find it, right? So this was again sort of proposed by Vladimir Stoyanovich and a few other people as well, where basically what they said is, okay, I've got one LMS loop that's basically just running to try and find what the equalizer coefficients are. In parallel with that, why don't I just run something that looks a lot like an offset cancellation loop to also find what the data reference level should actually be in the first place, okay? So that's what's called this DLEV, that's the data level. I've written here the sort of update equation. I think we wrote it last time, but what I actually want to do now is just sort of draw the hardware block diagram just to sort of make sure that it's kind of clear what's going on there. Okay? So basically, let's just keep in mind that we're going to have something that looks like essentially this. Okay, so we've got our sort of error that is going to be having some reference level that we're going to be setting to it. And of course, we're also going to be having just the data itself. Right, so the data itself, of course, ideally you'd like to set the threshold of that comparator to be 0. Okay? So now what we're going to do is we're basically going to say, okay, well, conceptually what we're really trying to do is just accumulate that error and then essentially feed it back through some digital to analog converter and use that to actually generate what is the sort of analog reference we use to compare against. Right? But there's one, let's say, minor, so-called unfortunate, problem with this particular drawing that I've used. So right now, if I do this, then notice each and every single time, each and every single sample, I'm going to be taking the output from that data level comparator and just, feeding it into this accumulator here, right? But remember, all we actually wanted to do was find what this upper level is, right? So what do I have to do to kind of make sure that what I'm actually finding is this upper data level and not just some other random thing that, in this particular case, actually God knows where that's going to land. So how do I find that upper data level? What do I have to do? How do I sort of modify this block diagram?
Gate for 1 data bits.
Yeah, so basically what I have to do is only when I actually have a 1 data bit, and I'll just draw this sort of conceptually for now. Only when I actually have a 1 data bit, only then should I actually be updating the value of my accumulator there, right? Because what I'm basically doing is I'm just saying, well, okay, if there's a 1 data bit, then I know that now the level should be at the point where I'm trying to look for it. So only in that case should I actually update the loop to try and find what is this analog value, right? You can imagine you could do something very similar where you could have another one that was looking for the lower data bit. But basically this idea of data filtering is a pretty important one because we're going to see in 1 second, you're going to have to play a sort of very similar trick to figure out how you're even going to adapt equalizers when you start doing things like loop unrolling. Okay? So the key idea here is that you basically, the way you find an analog level is you look for when is the data telling you that you should be at that analog level, and then you filter your updates based on that data pattern. Okay? Does this make sense to people, or? Okay, so now the question that sort of came up last time, which is sort of related to this, is that notice I'm now running like 2 loops in parallel, right? I'm running 1 loop that's always constantly updating what the data level actually is, and a second loop that's using that information or using really the error updates from here to adapt the equalizer, right? So the question that always comes up is, well, wait a minute. You've got 2 loops that interact. How do you know that they're really going to converge? Okay, and so the answer is I can't prove it to you, except that I have hardware that works, and I've got a lot of different hardware that works that says it converges. Okay? Yeah.
Just one minor point on the slide. I think that should be I of dk is equal to 1.
In this update equation, or?
Yeah.
Oh, yes, you are right. Thank you. So that should be this. There we go. Right. Everybody catch that? So this was just, that should have been when the data is a 1, only then you apply the updates, not the error being a 1. Okay, so as I said, it's really, really hard to prove that these things actually converge, but the good news is they really do. Okay, so the way this kind of looks as it's converging is sort of an interesting thing to see. In particular, this example that I'm showing you here is actually on the transmit side. So if this is like your original initial I with no transmit equalization, then what happens is you start adapting the transmitter. Basically, sort of two things happen, right? So one is I start doing a better job of equalization. So it looks like the I actually kind of opens up, right? I have less ISI. But the data level is actually coming down, okay? And notice that when I get all the way sort of equalized, then what should be happening is I'm kind of trying to drive the ISI as much as possible to be 0 around this data level. But notice this also gives me kind of the smallest level of that actual data. So maybe just as a reminder, why is it that, if I'm using transmit equalization like this, why is it that when I run this adaptation, I actually get a smaller data level than I used to? What's going on there?
DFE. It's EFE, which sacrifice swing to kill off ISI.
Okay, yeah, that's you're kind of saying it. So basically you said this is a zero forcing equalizer. Actually, even if it was MMSE, the trick is that because I have a fixed peak swing at the transmitter, when I start putting stuff into the equalization coefficients, by definition I'm attenuating the DC. Right? So that means that indeed the data level is just going to be coming down as I run that equalization. Okay? So that's exactly why you sort of see, there's actually a lot of movies that, sort of you see this eye kind of breathing in some sense. Like initially, you don't really know what the data level is, and so things move around a bit. And then once you lock, it sort of all smushes in. I guess maybe next time we'll actually bring that movie. But in fact, you guys will get a chance to do this because you'll be building a link that actually does the adaptation, at least in Verilog and things like that. So, maybe I'll force you guys to actually show me the movie at the end of the semester or something like that.
Might take all semester to run.
Say that again?
Might take all semester to run.
No, actually, this is not. Well, okay, so that's actually why. So you said it might take all semester to run. That's actually why we're going to be talking a lot about behavioral models at some point, because otherwise, indeed, it would take quite a long time for you to see this. The good news is, in terms of getting this behavior, behavioral models actually do a pretty good job from that standpoint. Okay, so this sort of plot here is just another way of saying that yes, please do believe me, it does actually converge. We tried this over a whole bunch of different, settings. So things like, we made one loop average 10 times more than the other, and then flipped it around. And basically, everything that you did, the thing still pretty much converged. That's not to say it didn't do weird things in between, but eventually it converged to the right value. Okay, so particularly in these applications where you don't care too much about the convergence time, that was basically in good shape. Okay. As I said, hard to prove analytically this really works, but indeed it does actually converge. Okay? So that's good news. There are, let's say, a few practical things that we do have to be a bit careful about, though. Okay? And the first one is actually something that we talked a bit about last time. And that's that when we really use this kind of algorithm, what we're basically assuming is that the sort of analog, let's say, spectrum coming into our receiver, if we don't do anything, is a good representation of what the channel actually looks like. Okay? Because if it's not actually a good representation of the channel, then if you think about it, when you run this sort of equalization that's just relying on looking at these correlations between the data, well, then what will happen is you'll start equalizing for something that's not really the channel, but just something that's actually related to the data pattern you were sending in the first place. Okay? So just to sort of see conceptually how this might happen, imagine that your channel actually looked something like this. Okay? Let's say, just some simple, low-pass kind of channel or something. And then let's say that instead of doing a good job and actually sending white data like I said you should, let's say that from whatever reason you started sending a square wave. And you sent it at some relatively low frequency. Okay? So what's the spectrum of that square wave going to look like? Yeah, just a bunch of discrete tones, right? So as an example, let's say that it, lands something like this, right? Okay, well, So kind of what's the, and it's not really an exact statement, but what's kind of like the effective channel that your receiver would see and try and equalize for if this is what you were sending?
I think you had a really bad channel.
Yeah, it would basically think you have a really bad channel, right? It would say something like, oh, okay, your channel sort of looks something like this, right? Now, again, what I'm saying is not exactly correct because it turns out if you really did this, things would kind of go bonkers because all of those statements I made about, D0 not being correlated with D1 would kind of fall apart. But in some sense, this is kind of saying, well, okay, you're somehow mimicking some other really weird-looking channel, right? And then it would go and sort of try and correct for this other weird-looking channel, which you can imagine that if all of a sudden you don't send a square wave anymore, you send actually some real data, now you're in trouble because you're completely misequalized, right? So this is indeed a sort of practically a fairly significant issue to worry about, especially if you look at systems that do things like, put some coding onto the data. So for example, something like an 8B, 10B code, which is just, something that guarantees transitions. But inside of those codes, they usually have specific patterns that are there just to tell you, oh, actually, I have no real data. I just have like an idle sequence. You can imagine I'm sending idle sequences for a long period of time, and I could be sending the same idle sequence for a long period of time. So now, in some sense, if I continue adapting my equalizer on that idle sequence, I'm going to have some completely bogus equalization settings. Okay? The good news is it's actually fairly straightforward to sort of at least not update when you know that you have bogus sort of, or when you know that potentially you'll be getting bogus directions for the update. So anybody have an idea of how you do that? What's a way of sort of knowing that the data you're getting is bad?
Autocorrelate the data.
Say that again?
Autocorrelate the data with itself.
Yeah, basically that's exactly what you do. You just check the data, right? You check, okay, is this data really white? Or does it actually have some spectral content in it that's not white, right? And the way you check that spectral content is indeed exactly what Matt was saying. You essentially autocorrelate the data, okay? So autocorrelate just means basically you take the data and you multiply it by shifted versions of itself. And if any of those shifted versions, times the original data on average has some either positive or negative value, that means you're not sending something that looks white. Okay? Because white, remember, means that the autocorrelation should just be like only the current sample should be correlated with itself. Everything else should be completely uncorrelated, right? So indeed, this is actually a paper by some of the Rambus guys. This is Brian Leibowitz from ISC 2007. This was basically exactly the kind of solution they proposed. They basically said, okay, in this example, I believe they had a 10-tap equalizer. So what they did is sort of over a window of data, they exactly calculated this autocorrelation, which, that's kind of what these little blocks here are. They're just saying, okay, I take, for example, the data, 10 bits ago, and I multiply it by the data 9 bits ago, and then I just accumulate it. And multiply here just means either XOR or XNOR, depending upon whether you're looking for the same data bit or opposite data bits. In this case, you're looking for the same, so it's XNOR. Okay? So then what they did is just, they run this accumulation over some number of cycles. And then if they see that, oh, oops, these things are actually correlated, they say, okay, throw out that update. Because you know that this is actually going to be a bad update. It's not going to give you a reasonable result. Okay? So to sort of see how this works and why this really is indeed a big issue, this is actually sort of two plots, and I apologize, it's a little bit hard to sort of see it, but basically this upper plot over here is kind of the trace of the adaptation curves in terms of what you would get if you didn't do something like this. They called it spectrally gated adaptation. Basically, if you didn't do something to try and fix this problem, you just ran the adaptation no matter what the incoming data was. Okay? And then this bottom trace over here, that's what happened when you actually include this hardware. Okay, and so the way to sort of read these time axes is, for some period of time, they're sending 2 to the 31 PRBS data. Then, for some other time, they're sending some static pattern, as an example, an idle sequence. And then again, they're sending some 2 to the 31 PRBS data. Okay? So what you can kind of see is that if you don't take care of throwing away bad updates, all of a sudden, while you've got that static update, you're converging to something completely different. Right? Each one of those traces is just going off and bonkers and just doing something weird. Right? And then eventually, when you get the real data again, it sort of, maybe converges to the right spot. Whereas notice here, when they actually include this spectral gating, basically, once you see that the data is bad, You just throw all those updates out. You basically don't change your coefficients at all. And then, of course, if the channel itself is changing, well, sorry, tough luck. There's nothing you can do about that. But at least you know that you're not going after something that's really bogus, right? And then, of course, once the real data starts again, well, OK, then you start tracking and dithering around kind of that nominal value. OK? Does this make sense to people, or? Yeah.
As long as you are doing the online tracking, even if you go into some, not so good status, you're still fine, right? You can see that you're going back to.
No. So here's the problem. So you said that as long as you're doing online tracking, then you should still be OK, right? Well, here's the problem. Those data bits right there have really bad equalization settings.
So you mean the first few?
Exactly.
bits
So the first few after I start getting real data have really bad equalization settings, right? Which means that I'm very likely to make mistakes, and if I've made a mistake, that's it. I've lost my 10 to the 15 bit error rate, or in fact, even people want 10 to the minus 17 now, because there's sort of like a fixed number of errors you want per unit time, and if you're going faster, then the error rate just keeps having to go down. Yeah.
I was wondering, can you just say XOR your sequence with like a known long pseudo-random sequence to like avoid this problem?
OK, that's a great question. So it turns out that what Igor was saying was, can you just take your sequence and basically XOR it with some known random sequence, and then hopefully that known random sequence is different than your data, and so you should sort of guarantee that things are sufficiently random. That's indeed actually something very common. That's what's called scrambling. That's a very, very common technique, both in Ethernet, actually even wireless systems and things like that. Indeed, that's something that is fairly commonly applied. The only bad news is that if you do something like that, it does put a little bit of extra burden on the receiver on the other side, because you have to sort of find, OK, where in this scrambling sequence am I actually sitting? Did I start here? Did I start there? It's not too big of a deal, but indeed, that is actually a fairly powerful technique. There is still the sort of, let's say, this is a lot, let's say, like the dual loop convergence, where if you do the scrambling trick, then you really have to hope and pray that your real data is not correlated with the scrambling sequence. Practically speaking, that's usually OK. But there's no guarantee, so to speak, there. It's a great question. Yeah?
The static data happens during the 8-bit, 10-bit decoding as well.
Yeah, so this is just an example in that specific sort of protocol. 8-bit, 10-bit coding is sort of done for two reasons. One, it's to guarantee sufficient transitions. But two, remember, if I have some PPM offsets between the transmitter and the receiver, I kind of need to know when is it OK for me to just throw things away and not even update, not even shove it into the FIFO. So those idle sequences are saying, OK, there's no real good data here. So don't even bother putting it into the FIFO, just throw it away, right? Well, if we're idle for some reasonable period of time, then it's just going to keep repeating that same idle sequence. Does that make sense? Or?
Yeah, I was just wondering if the common mode does, since everything is differential and I'm assuming it's all high-pass filtered, then if there's a long static sequence, then doesn't it cause problems on the receiver?
Oh, OK. So you're asking, like, if I already had a high-pass filter somewhere, then that already says that I can't have frequency content below some level. That is true. But remember, I could be sending a square wave, which has no DC content, and still have problems, right? Because it's just the fact that the sequence is repeating and not white that's really causing this issue.
Yeah, just talking about this specific case.
Yeah, so it turns out the idle pattern doesn't have DC content, but it's still repetitive. And so because it's repetitive, that's what's causing the issue. Chris?
Can you have idle patterns that look roughly white, like a bunch of evenly spaced tones that are
Yeah, so if the idle pattern was long enough relative to sort of the equalizer that you were trying to adapt, then you'd be OK. Right? So if your idle pattern was, let's say, 100 bits long or 200 bits long or something like that, and your equalizer was, I don't know, 20, maybe even up to 50 bits long, then you're kind of OK. Right? The problem is, for example, if I have 8-bit, 10-bit coding, my idle pattern is 10 bits long, and my equalizer is also 10 bits long. And so then I'd really start having a problem. But you're absolutely right. If it's sufficiently white over the length of your equalizer, then you're OK. That's actually kind of why this autocorrelation trick is nice, because you do that autocorrelation only over the length of time you know matters for your particular equalizer. It's a great question. More questions on this? Or?
So something like this is practically necessary to get real.
Yeah, so obviously it really depends on the exact usage scenario. So some links, they only even run the adaptation during some, let's say, training period of time, or maybe they have known training periods where they know that they're going to get white data in them. But yeah, for a lot of, let's say, a lot of practical applications, something like this is indeed necessary just to make sure that you kind of don't go bonkers. some of this is, well, I shouldn't say going away, but there are obviously other things you can do, right? So as an example, let's say you really know that you're idle. Rather than continuously transmitting idle patterns, you can try and do something like actually shut the link down, right? Which, from a power standpoint, in theory, should also be a good thing to do, right? Now, because of various reasons, people don't like to do that or have been reluctant in the past to do that, simply from the standpoint of then when you start it back up, you have to guarantee that everything locks quickly and still has low error rate and things like that. But that's starting to happen simply because you can end up spending a lot of power in something like a big server somewhere where a bunch of these links are basically just spending hundreds of milliwatts or watts just sending I'm idle, I'm idle, I'm idle, I'm idle at 20 gigabits per second. So yeah, it's a great question. Practically, you do indeed tend to do this, but maybe there's some other, let's say, system level solutions you can come up with as well. Okay, so the next thing I want to talk about from, let's say, a practical standpoint is exactly what Richie was asking about, which is, even after you do all this, remember there's only going to be some, finite DAC resolution you're using to actually set these coefficients. So even if you had like a perfect estimation engine in the back end, there's no way you could exactly set the value to be what you wanted it to be. Okay? And practically speaking, given that you're sort of putting this integration into there, what those integrations will tend to do is make it so you kind of jump back and forth between the different values close to the real value you actually want to get to, right? So that kind of on average, you roughly speaking get the right value. Okay? So what that means is that indeed, if you look at each one of these little tap values here, they're always going to have some amount of dither on them. Okay? Now, you were asking earlier about, well, do you just freeze it or something like that? You could indeed freeze it, but it turns out if you looked at, let's say, the mean squared error or the expected error that you'd get from doing that, it's no different from having the dither. Because you don't really know where you stopped, and so on average, you get about the same amount of error as you jumping around back and forth. Okay? This does have some very important implications, though, because it says that if you start doing a system with lots and lots of these taps, you really better include the sort of variation on those taps in your error budget, right? Because you can imagine each one of them, even if it has some small error, when you add all of those taps up, even if they're independent, the variances are going to add up. Okay? So kind of to say this another way, there's always going to be some quantization noise just from sort of the resolution with which you use to actually correct that ISI. Okay? And the more taps you have, the more resolution you need in each one of those taps to get the same effective quantization noise. Okay? Does that kind of make sense to people? Again, this is actually a pretty important practical issue, which initially some people ignored and just said, okay, I'll go ahead and build like a 20-tap DFE, each one with like 3 bits of resolution, and of course, immediately everything just barfs on you, right? Because you just get tons of noise just from dithering all the DFE taps and not even from actually doing anything useful. Okay? So it's indeed a very important issue to just keep in mind. Okay, so unless there's sort of more questions on that, the last thing I want to just briefly mention is, remember we talked about how once you push things to high enough speeds, you end up trying to do things like these loop unrolling types of tricks where you try and push that critical path in the first DFE to be somewhere in the digital domain where maybe you have less penalty from the standpoint of doing the analog settling and things like that. So just as a reminder, I'll sort of draw one of these things just so that everybody remembers. All right, so as an example, let's say for the first tap, you'd build it as something that looks like one comparator with plus alpha, another comparator with minus alpha, and then something, that's your input data pattern, right? And then what you do is, of course, once you know what the right data bit is, then you actually select which comparator you should be looking at. Okay, just as an example, let's say 1 and 0 like this. Okay? Okay, so now, turns out this has some unfortunate consequences when you actually try and do the adaptation. Okay? So remember, to do the adaptation, what I had to do was add another comparator here like this, with its threshold sitting at the data level. Okay? Now, my claim is that if you do something like this with a loop unrolling, I'm not actually exactly sure what I even mean when I say the data level. So what's the problem? Why is it that there's this issue with what is the data level in this kind of system? I'll give you guys a hint. If I actually looked right here at this analog input. What does the channel up to that point look like? Somebody other than Chintan, because I know he knows the answer. So let's say I have, a perfect equalizer and everything, doing everything that I want all the way up right until that point. And then the only thing I have left to do is just this loop unrolled DFE that's canceling that last first post-cursor tap. So if I looked at the channel from the transmitter up until this point right here, what does that channel look like?
Sort of 4 possible levels, right?
Ah, okay, so you said there's 4 possible levels. In other words, the channel up to that analog input is something like 1 plus alpha, right? There's some residual amount of ISI that I've intentionally left there because I know that I'm going to be canceling that through this loop unrolled DFE, right? Okay, so if you think about it as we've said before, right, this bit can be plus minus 1, this bit can be plus minus 1. So now I've actually got 4 possible data levels, okay? So now I know I said before that this looks kind of weird, but now we're actually going to go ahead and draw it. Let's see what the eye diagram for something like this actually looks like, okay? So in some previous data sample, again, and I'll just draw it maybe a little bit bigger, I could have had 4 possible data levels. And of course, in this data sample, I could also have 4 possible data levels. Okay, but now, how do I what transitions am I allowed to make? So let's say that I used to be at this upper data level, which remember is just plus 1 plus alpha. From there, where can I go? What could the next value be?
Plus 1 plus alpha or minus 1 plus alpha.
Yeah, exactly, right? The next value could be either I just stayed again to be a 1, so I just stay at the same place, or if my next bit is a 0, then I basically transition down to here, right? Okay, so of course everything's symmetric, same thing happens on the bottom, right? So I do something like that, right? Okay, now if I'm in this inner level here, so remember this is 1 minus alpha, where can I possibly go from there? What can happen? I'll give you a hint. There's 2 possibilities. So
Same place the top bar goes.
yeah, so you can either go up to the top, right? Because if you have a 1 again, then that residual alpha will just resolve itself out, right? And by the way, obviously the eyes don't really look exactly like I'm showing, but kind of roughly speaking. So of course, symmetrically, the same thing could happen on the bottom. But what else can happen if I start from this level here? Where else can I go?
Go to the plus 1 minus alpha.
Almost. So you said plus 1 minus alpha. I think you mean minus 1 plus alpha.
Oh yeah, that they cross, I guess.
Right. So you mean like this. Right? Those are basically the clock patterns. Okay? So actually, I'm just going to complete this thing so we have an entire eye. Obviously, it's the same thing on the next data bit. So that, of course, this completes, that completes. This goes up like this and down like that. This goes down like this and up like that. And from here, we also get this and that. Okay? So now this funky looking thing that I've drawn is indeed kind of the eye diagram going into your receiver now. Okay? So now, when I say that I should set my sampler to the data level, what do you think I mean by that? Or what do you think you're going to have to do to actually get any kind of information out of this thing? Where should you set your sampler to find the errors? And I'll give you a hint to find the errors for all of the taps except for this one that I've loop unrolled. Where should I set the reference level? I'll give you a hint. There's no one answer, but there are 4 answers that are correct. So what are the 4 answers? Remember, what was I trying to do with this data level? What am I trying to figure out from that?
What alpha is?
Okay, so there's actually two things that I could be trying to figure out. I could be trying to figure out
Direction of the error.
what is alpha, right? I could also be trying to figure out what is all of the other coefficients, right? So in other words, what is beta, gamma, etc., right? Because remember, I'm going to have probably some transmit equalizer. I may have some more DFE taps that I need to deal with, right? So actually, I need to figure out both of those things, right? And of course, the second one is really multiple tap values. So actually, let's see. What do I do? I mean, if you guys can figure out how to do this one is actually, the first one is actually more complicated, which is why I asked about the second one first. But you know, if somebody wants to figure out the first one, then that's fine with me too. So how do you figure out where to put the data level for either one of these two? Or just in general, how are you going to figure out those values? Can anybody come up with a hack for number one at least?
Just put it at the highest level.
Okay. So indeed, I could put it up at the highest level. And then what?
And then when both of the comparator gives you 1, you take the comparator error.
Okay, that's actually right. So now, by the way, are you trying to figure out what alpha is, or are you trying to figure out what all of the other taps are? Okay, well, so unfortunately, I'm not sure I can actually find alpha from this. But you are right that I could take the comparator. I could filter for when did I get a 1-1 sequence, right? And then only update the threshold on the 1-1 sequence. And I would indeed find this upper level.
That's for all others. That's
Say that again?
That's for beta, gamma, and so on.
Yeah, that's right. So now you're right. If I put my threshold level up over here, then indeed I could find all of the other taps simply by using this as my reference level. Because remember, all of the other taps, they're like, it's a linear system, right? So the errors around this reference level are the same as the errors around this reference level, right? So in other words, I can choose any one of these 4 reference levels, and as long as I filter my data to find that one reference level, and then I look for all of the rest of the taps around that reference level, then indeed it should work. Okay? So that actually answers how you do number 2. So for number 2, you just filter the data to find any one of these 4 levels, and then indeed you can close all of the same LMS loops we talked about before to actually adapt all of the rest of the equalizer coefficients. Okay? So that indeed works. Now, how do you answer number 1? How do you find alpha? And by the way, this is, this exact question is why I'm not the biggest fan of loop unrolled DFEs, but we'll come back to that later. I'll give you a hint. It's a hack. Yeah, go ahead.
Can you filter for like 1-1 and 1-0 and then average the voltage level?
Okay, so is it the average of them, or is it something else that you actually would do?
Midpoint.
Ah, there we go. Okay, so you could filter to 1-1. You could then filter for 1-0, right? Turns out so it is sort of the average, but to be more precise, remember this analog voltage level here is 1 plus alpha. This one over here is 1 minus alpha. So if I want to know what alpha is, then basically I have to take the difference between them and divide it by 2, right? So in other words, that spacing there is indeed 2 alpha. Okay? Now, I said before I actually am not a big fan of doing this, but there's a reason why I'm not. I mean, it's not that you can't actually do it. There are ways of doing it, but it has some pretty, let's say, stringent implications on how you actually build this. So why is it that finding things this way can actually be kind of nasty? What does this imply about sort of how you have to build this whole system? I'll just give you guys one hint. Remember that for all intents and purposes, the way we're going to find those alphas is by driving some digital code into a DAC. Okay? So when I say that I want to find the difference between 1 plus alpha and 1 minus alpha, what is it that I'm actually doing? Like, what operations do I implement in the digital domain? How do I find the difference between two things?
A subtraction
Okay, so you do a subtraction.
at the bit rate.
Okay, I won't actually do this at the bit rate because hopefully the channel's not changing that fast, so maybe I do it at the deserialized rate. Okay, yeah, there's some power from doing that, but let's not even worry about that because, by the way, like I said, this kind of has to be a hack because I have to sort of jump between one level and the other level. So while I'm doing that jump, I probably don't want to be adapting all my other stuff. So maybe I even do this sort of offline. Okay, so yeah, I have to do a subtract, and then I do a divide by 2, right? Okay, so my digital operations, those are digital. Those work perfectly. What happens in the rest of the system? What do you do with those digital coefficients? What do they get fed to?
DAC.
Yeah, they get fed to a DAC, right? Okay, so now, and this is maybe just a reminder, if I really had a loop that, and I'll just go back to this hardware block diagram we drew over here. If I really had a loop like this, what's the only thing I care about from this DAC? What's the only thing that matters when I'm actually actively updating it like this? What's the only sort of, let's say, design constraint on that DAC?
Monotonicity.
Okay, yeah, probably I want it to be monotonic, right? And maybe I want it to have a sufficiently small step size, right? Okay, well, what happens when I take this same DAC, which just as an example, maybe its codes, code versus voltage looks something like that. What happens when I take that DAC and I do A plus A minus B divided by 2? Am I going to land anywhere near where I actually wanted? Well, it depends, right? Maybe if I was over here, I got lucky, but if I spanned any of these codes like this, I'm in trouble, right? And especially if the DAC was, had a bad nonlinearity or something like that, guess what? When you do A minus B over 2, you're completely way off the ballpark, okay? So the real reason why, again, I'm actually not the biggest fan of this particular implementation, although sometimes you just don't have a choice, is that if you do this, you better make sure you build a super duper linear offset DAC, and to go along with it, another super duper linear DAC that creates the DFE correction. Because there's no closed loop thing that actually drives you to the right spot. Okay? Yeah?
I do have a question about that. The thing was, you do have like a summation after the comparator. That thing was kind of like a low-pass filter, so essentially kind of help you averaging out everything, including this mismatch from the DAC.
Okay, so here's the problem. Remember, I'm running this thing at 10 gigabits per second. So if there's a big enough low-pass filter at that summing node, or 20 gigabits, or whatever frequency that I'm running it at, right? If there's a big enough low-pass filter that I'm actually averaging these DAC corrections out, guess what? I'm completely averaging the data out too, and then I'm making mistakes, right? So unfortunately, it's not like, okay, so the only way you could do it is if you actually put an analog low-pass filter sort of in the voltage domain in front of that DAC that was not interacting with the signal. And then you could do some, let's say, filtering or something like that, but again, remember, when I do that A plus B over 2, there's nothing really driving me to the correct center point, right? Because all I know is the digital code associated with this level and the digital code associated with that level. That's not to say that the digital code associated with what's in between is even on average the right value. You see what I'm saying? Or, yeah, so again, that's not to say that you can't build a super linear DAC and that you can't get this to actually work. It's just that if you do, you better be really, really careful. Because, by the way, this particular issue has actually bitten all kinds of people when they didn't think about it. Okay? So really the big difference here between everything we've been doing so far is that there's no real analog voltage level that you can filter the data to find what the right value for alpha is. Right? In all of the other things, we had basically these closed loop systems that would drive some error value to 0. And that when we got that error value to be 0, we knew that we were at the right spot, independent of sort of what the transfer curve of the DAC was. Here, no closed loop thing you can really do. All you can do is just go from this point to this point, and then rely on the DAC being sufficiently linear. If it is, then life is good. Yeah.
What if you use two comparators to get the D plus alpha and minus alpha, and then just pick the correct one to do the error calculation depending on the data.
Well, but that's the unfortunate problem is these two DLLs, 1 plus alpha does not put me at alpha, right? And the threshold I need for this one is plus alpha or minus alpha. So there's no analog level at plus alpha or minus alpha anywhere, right? Do you see what I'm saying? Or?
I think so.
So in other words, if I wanted a threshold at plus alpha or minus alpha,
No, I mean at 1 plus alpha and 1 minus alpha.
right, but so all I can do, well, maybe I misunderstood what you're saying. If I find 1 plus alpha, if I don't know the DAC sort of transfer characteristic perfectly, that doesn't tell me where alpha actually is.
So I mean have two, the way you were talking about it now, the one comparator that you have looking for DLEV, you switch between.
Oh,
like
I'm sorry.
one
Okay, so
physical
yes,
I mean,
you
use
could
two
indeed
physical
have two of these, right?
Yeah.
But you'd still actually have the DAC problem. And the reason for that is, even if I have two of these, that just means I don't have to hack it, meaning I could actually run this sort of quote-unquote live. But notice there's still no closed-loop feedback that's telling me that the alpha level I'm setting here is actually the right alpha level.
But I guess if you have the two DLEV comparators running continuously, can't you get alpha using the way you used to get alpha before it was unrolled?
Unfortunately, no. So, and here's the reason why, right? Before, what we were actually doing was we were taking this analog eye diagram, right? And so if there was some residual error around that level, you'd see it as the data level comparator saying on average, oh, there's something above me, there's something above me, there's something below me, or something like that, right? Notice here, if I shifted this alpha level around, let's say, instead of over here, I actually put it there. The data level comparator doesn't know squat, right? Because that doesn't move the error around the data level. That just means that you're more likely to make a mistake on the data. Do you see what I'm saying? Or so in other words, let me say it a different way. Let's say that, over here, I'll do it right there. Let's say that over here, let's say for some reason the threshold of my comparator was right here. Can I adapt this thing to fix the threshold of my comparator? Or no? Does the data level error tell you anything about the comparator threshold error?
No.
Doesn't, right? So that's the problem, right? Because basically, I don't know what the real comparator threshold in this point is either. All I'm doing is I'm assuming that there's some good mapping between what my data level is doing and where my comparator is actually sitting. But because I don't have a closed loop way of doing it, I can't actually enforce that. Yeah?
Well, I was just thinking about when you say there's no closed loop way you can actually doing this. What happens you trying to do those doing interpolation between this 1-1 comparator and the 1-0 comparators?
That's right.
Maybe you can actually create like intermediate levels and you can actually using that level to close your loop. Would that be possible?
Well, again, unfortunately, no, because the problem is there's no, I guess the only thing I could think of to do would be to literally take some weird analog circuit and try and construct the analog alpha level. But I'm not even sure how I'd do that either, because to do that weird analog circuit, it needs to also have some programmable offset that I'm not, that I think will have the same problem in terms of adapting it in the first place. Right? So, if you guys can find a way to solve this problem, great. Unfortunately, I don't think there is a way to solve it, just because, basically it all comes down to there is no real analog level that you can filter the data to find where that value is actually sitting. All you can do is find things that have summations of that analog level with other things. Okay? Now again, that's not to say that this doesn't work. It just says if you do it, better have a really, really linear DAC. In fact, multiple very linear DACs so that you can take a code from one DAC and use it as a code in another DAC and expect that they actually match each other. Okay? Does this sort of make sense to people, or? I see some slightly skeptical looks, so.
So when you say you subtract and then divide by 2, you're doing that operation on the digital code?
Exactly. I'm doing it on the digital codes, right? Which does not mean that I'm actually doing it on the real analog levels at the output.
Yeah.
Right? Because again, all I have to estimate here is the digital code values, right? So okay, actually, maybe you gave me a thought. Maybe there's some weird analog sample and hold thing you can do, but even that, that seems pretty tough, right? Okay, actually, maybe you can get that to work. But anyways, point being, if I really want this, driven by a digital control loop, better build a good DAC, right? So again, good and the bad news is, or rather I should say the good news is, you can indeed build really linear DACs. It just costs you a lot more to build a really linear DAC than it does to build a crappy DAC that just happens to be monotonic. Okay? Okay, great. Any other questions on this? Or? So looks like we're out of time for today. So for next week, we'll actually dive into timing and PLLs and things like that. So we're finally done with the journey of equalization. So I'll see you guys next week.